Hello, everyone. Today, we're going to understand two very important concepts in electricity: Ohm's law and electrical resistance. These ideas are really the foundation for understanding how circuits work, so let's make sure we get a very clear picture of them together. So here is our plan for today's lesson. We'll start with a quick recap of the basics, then we'll dive straight into Ohm's law to understand its VI relationship. After that, we will explore this idea of resistance, what it is, and what factors affect it. We'll also clear up a common confusion between resistance and resistivity, and finally, we'll solve a numerical problem together to put everything into practice. All right, so before we jump into anything new, let's just quickly recall two key ideas. First, we have electric current, which we denote with the letter I. And what is it? It's simply the flow of electric charge through a wire. And the second idea is potential difference, or voltage, which we call V. You can think of voltage as the electrical push or pressure that makes the charges flow in the first place. Now, with that in mind, I have a simple question for you. Just think about it. If we have a wire and we increase that electrical push, the voltage, across it, what do you think will happen to the flow of current? Will the current increase? Will it decrease? Or maybe it will just stay the same? Just keep that thought in your mind for a moment. Well, it turns out this is the exact same question that a German physicist, Georg Simon Ohm, investigated way back in 1827. He wanted to find the exact relationship between the potential difference, V, and the current, I. And this is how he did it. He set up a simple circuit, just like the one you see here. He took a nichrome wire, connected it to an ammeter to measure the current, and a voltmeter to measure the potential difference. First, he connected only one cell, and he wrote down the readings for V and I. Then, he connected two cells in series to increase the voltage and measured the new current. He did this again with 3 cells and then 4 cells, carefully recording the data each time. So what did he find? Well, when he plotted his results on a graph, with potential difference V on the vertical axis and current I on the horizontal axis, he got a perfect straight line that passed right through the origin. Now, from your mathematics classes, you know what this means, right? A straight line graph passing through the origin tells us that the two quantities are directly proportional to each other. As V increases, I increases in the same proportion. And this amazing discovery is what we now call Ohm's law. Let's state it properly. The potential difference, V, across the ends of a given metallic wire in an electric circuit is directly proportional to the current, I, flowing through it, provided its temperature remains the same. Now, this last part is very important. The law only works if the temperature of the wire doesn't change. So, mathematically, we can write this relationship as V is proportional to I. Now, you know that to change a proportionality into an equation, we have to introduce a constant. So we get V is equal to some constant, which we call R, multiplied by I. Or as it's famously written, V equals IR. This constant, R, is a property of the conductor called its electrical resistance. So a new term has come up, R, or resistance. What exactly is this property? What do we mean by electrical resistance? Let's take a closer look. Well, the name itself gives us a very big hint. Resistance is the property of a conductor to resist, or to oppose, the flow of charges that are trying to pass through it. It's like an obstacle in the path of the current. Let's use a simple analogy. I want you to imagine you are trying to walk through a very crowded school hallway between classes. It's difficult to move, isn't it? You keep bumping into other students, and it slows you down. That crowd is offering resistance to your movement. Well, something very similar is happening inside a wire. The electrons are trying to flow from one end to the other, but the wire is not empty. It is full of atoms. So as the electrons move, they are constantly colliding with these atoms. These collisions get in their way and slow them down. This opposition, this hindrance to the flow of electrons, is exactly what we call electrical resistance. And of course, we need a unit to measure resistance. The SI unit for resistance is the ohm, and we use the Greek letter omega as its symbol. So what does 1 ohm mean? Well, we say a conductor has a resistance of 1 ohm if a potential difference of exactly 1 volt across it causes a current of exactly 1 ampere to flow through it. See, it all connects back to V and I. So the next logical question to ask is, does every wire have the same resistance, or does it depend on the wire itself? Let's find out what factors affect the resistance of a conductor. It turns out that resistance depends on four main things. First, the length of the conductor. It's quite intuitive. A longer wire will have more resistance, just like a longer crowded hallway is harder to cross. Second, its area of cross-section, which means how thick the wire is. A thicker wire has less resistance because there's more space for the electrons to flow, just like a wider hallway is easier to walk through. Third, the nature of the material itself. A copper wire will have a different resistance than an aluminum wire of the same size. And finally, as we mentioned before, temperature also affects resistance. We can put all these ideas together into one formula. Resistance, R, is equal to rho multiplied by the length, L, and divided by the area of cross-section, A. Now this new symbol, rho, which is a Greek letter called rho, is another constant. We call it the resistivity or specific resistance of the material. Okay, this brings us to a point which often confuses students. What exactly is the difference between resistance and resistivity? They sound so similar, but it's very important to understand that they are two different things.
Let's break it down with this table. Look carefully. Resistance, R, is a property of a specific object, like a particular piece of wire you are holding. It depends on that wire's length and thickness. But resistivity, rho, is a property of the material itself. For example, all copper has the same resistivity at a certain temperature. It doesn't matter if it's a long wire or a short wire. So resistivity only depends on the material and the temperature. And you can also see their units are different. Resistance is measured in ohms, while resistivity is measured in ohm meters.
You know, the best way to make sure we have understood these formulas and concepts is to apply them. So let's solve a numerical problem together. Okay, let's walk through this step by step. First, step 1, write down what is given. The resistance R is 26 ohms. The length L is 1 meter. And the diameter, D, is 0.3 millimeters. Now, the first and most important thing to do is convert all units to the SI system. So 0.3 millimeters becomes 3 into 10 to the power of minus 4 meters. We need to find the resistivity, rho. Step 2 is the formula. We know R equals rho L by A. We need to find rho, so we rearrange the formula to get rho equals RA over L. Since the wire is circular, the area A is pi d squared over 4. Step 3 is to substitute all our values into the formula. And finally, step 4, after doing the calculation, we get our answer. The resistivity of the material is 1.84 into 10 to the power of minus 6 ohm meters. So, let's just quickly recap the key takeaways from today's lesson. First, Ohm's law, V equals IR, which is the relationship between voltage, current, and resistance. But remember, only at a constant temperature. Second, resistance, R, is the opposition to the flow of current. Third, this resistance depends on the dimensions and material of the conductor, given by the formula R equals rho L over A. And finally, resistivity, rho, is a fundamental property of the material itself. We have built a really solid understanding today of how a single resistor behaves in a circuit. But in real life, in our phones and computers, we rarely use just one. So that leads to a question for you to think about. What happens if we connect many resistors together in a circuit? How do we calculate the total effect? That is exactly what we will explore in our next lesson.